so focused on such a tiny part of it, and that's for good reasons. And we're just now beginning to understand that all the variations that we're seeing could be really important in some ways. And that's the other piece of it. The variation is so much greater than we've ever dreamt. So around the same time, about a year ago, this project called the 1,000 Genomes Project came out, which was looking at the full genomic sequence of, in this case, the first 185 people. It's more than that now, all healthy. And they all had large numbers of mutations. Every one of us has mutations. In fact, every one of us has changes in our genomes that we have that our parents didn't have at the rate of about 50. Each of us has probably on average about 50 de novo spontaneous mutations. If we had parents that were over the age of 40, the number is more like 200. And most of the time, that doesn't matter. Some of the times it does. Some of the time, it's great because that is what makes you special and different. Some of the time, it's what puts you at risk for various kinds of medical and psychiatric problems. What is, again, stunning is that many of us have those kinds of mutations that have actually knocked out genes entirely. And yet, we seem to get by without too much trouble. So genetics is getting really, really complicated because now we're beginning to understand there's enormous amounts of variation. Much of it we don't understand. We have to figure out what variation really matters. And it turns out that even the way we think about heritability has to change. So just to summarize, and this could be a much longer discussion, it's so interesting because things have changed so much so quickly. We have to get away, or have to sort of rethink some of our terms. So when we say that something is genetic, that doesn't necessarily mean that it's inherited. That's a really fundamental change in what we think. There are lots of people, especially people with neurodevelopmental disorders, who have a genetic illness that they didn't get from their mom or their dad, in the sense that their mom or their dad had that same mutation. Maybe it was in mom's egg, maybe it was in dad's sperm, but it wasn't in their germline. So they didn't have it in their blood cells. But it's something that happened over the course of their parents' development, perhaps their parents' embryonic development 30 years earlier, that they then transmit in a sperm that has a mutation, or an egg that has a mutation, that emerges then de novo in the child. So it's genetic, but it's not inherited in the classic sense. A lot of genetics isn't about cause anymore, but it's more about risk. And when we think about these common variants, which have been around in the population for thousands of years, which all of us have many of, they don't actually cause illness as much as provide a kind of background for it in terms of risk or resilience. And we have a lot more to learn about epigenetics. And that is another field which is just emerging. Over the last month, a paper came out demonstrating that the way that the brain does epigenetic regulation doesn't look anything like the rest of the body. So the brain has its own bizarre system for for translating experience into changes in gene expression. Who knew? None of us knew this up until just about a month ago. So this is going to be a really interesting period to explore all of this. Finally, I just mentioned before about developmental disorders, and we'll take you through this very, very quickly, but the idea being, again, that we can begin to understand even illnesses like ADHD in terms of the way the brain develops. On the left, children with ADHD. On the right, typically developing kids. You can follow the age here from age 5 to age 12. I'll start this again so you can see it. I won't tap anything, so it'll keep running. That's age 8. Okay, age 9, age 10. What's filling in is points of maturation in the cortex. And what you can see, without taking a lot of time to show it to you again, is that essentially kids with ADHD just lag behind about 2.5 years, particularly in prefrontal cortex. They ultimately catch up, but there's this just really interesting variation.
Excuse me, what are the colors coding?
I'm sorry?
What are the colors coding?
Oh, thank you. Yeah, that's what happens when you go too fast. I didn't explain it. So this is work from our intramural program, and the darker the area means that you've reached the point of gray matter maturity So this is looking at gray matter density, gray matter thickness in the cortex. And so you're basically filling in, and what you see is the latency with the kids with ADHD. And the only reason I'm really showing you this is, again, this is around rethinking how we approach this. ADHD, attention deficit hyperactivity disorder. And yet, these differences are really profound. Like 10 to the minus 23 difference between these curves. This is not a minor or subtle change. They're just as profound as behavioral differences. And yet we're defining this not as a disease of cortical maturation, which it obviously is. We call it by its behavioral and cognitive symptoms. That would be like saying that ischemic heart disease is a chest pain disorder. And it is. It is a chest pain disorder. But as long as you stay at the level of chest pain, you will never begin to understand how to help people who have that problem. Because you're not at the level that you can intervene in a very successful way. So understanding this raises a whole series of new questions for you. What's the driver here? Why do some kids have the delay? How do you move that curve? A whole range of things that you wouldn't begin to ask if you're still thinking about the chest pain, the manifest symptoms. So that's the real quick overview of where I think the field needs to go if they're really going to begin to make the inroads that we need in terms of a different conceptualization about mental disorders. What really we need to be focused on is diagnosis and treatment, though, and that's what all of us care about at the end of the day here. What does this mean in the clinic? And I should hasten to point out that none of this is actionable in the sense that we're ready to use those kinds of brain images to diagnose kids with ADHD or any of the genetics to identify new therapeutic targets. But we do have to still transform both the diagnosis and interventions because neither one of them is working for us. And I think if there's nothing else I convey, and I don't want to do this in a way that sounds either dismissive, insulting, or depressing, but we have to realize that it's just not working for us. The fact that the numbers tell us that the public health metrics tell us that we aren't doing well enough for people with really bad diseases, say that we've got to think about a different approach. So in the case of diagnosis, we're borrowing a page from the folks in the cancer biology space, in oncology. The National Academy of Sciences released this report about 2 years ago called Towards Precision Medicine, which is very interesting about how they want to get away from diagnosing cancer by the organ of origin. In fact, we do not use the term breast cancer very often, or ovarian cancer, or prostate cancer very much in NCI. We now talk about what particular molecular diagnostic would that particular tumor have. And the reason we do this is because by knowing the molecular diagnosis, you know what the intervention should be. And if you follow mortality or you follow morbidity of cancer, you can see that real changes are happening in those areas where we have interventions that are specific to the molecular diagnosis. And we have that certainly for breast cancer. And we're getting it from lots of others. It's a spectacular time right now in cancer biology. In our field, we've tried to create something that's parallel to precision medicine called the Research Domain Criteria. I mentioned this RDoC. And the RDoC project is actually very simple. It simply says it's really important to listen and to watch and to get the presenting symptoms and signs from anybody who walks in the door. But don't stop there. Think about all the other levels of information that could inform what you need to know about this person. Because to look it up in DSM and give them a label of major depressive disorder tells you about 3% what you need to know. Those diagnoses are useful. That is, the categorical diagnoses that we have in DSM are great for reimbursement. They are not so great for understanding the problem. And to understand the problem, just as in cancer or any other area of medicine, you need to know something about the underlying biology, you need to know something about the cognitive structure underlying the symptoms, you need to know a lot about the social networks in which this is all embedded. There's a whole level, there are many, many levels of information beyond presenting symptoms and signs, which is the only thing that you're going to find in DSM. So RDoC is an attempt to put all of that together and to ask the question about when, as we take the current diagnostic categories like depression, schizophrenia, bipolar illness, and we begin to deconstruct them, blow them up, and figure out, is this actually one thing or is it many things which require different interventions? Can we do that by looking at all these different levels of information, imaging, genetics, cognition, social structure, and if we reassemble this, will it come back in a very different form that might be more useful for developing interventions? So just one example, if we think about depression, all of the various aspects, just at the level of cognition and behavior that one could ask about in trying to understand this very heterogeneous syndrome that we call depression. Once you've done this a little while, you realize, my goodness, what were we thinking? This really is like saying chest pain or fever. It's so many different problems. It's not helpful in identifying interventions. It's no wonder our clinical trials are very promising, because it's like trying to treat everybody who has a fever with an antibiotic. You're not going to do very well unless you have other kinds of information besides the body temperature to identify who might get better with an antibiotic and who might not. So this is an attempt to, at least at one level of cognition and behavior, fill that in. And then we want to do that at many, many different levels, from genetics to circuits to physiology, right on up. But I just mentioned the cognition because it's one that we can probably begin to grab already. And what we already know is that many of these features or dimensions of behavior that might even cross the current diagnostic system. So RDoC is a way of sort of freeing us up, saying, let's think about going deep on these problems and understanding these as dimensions of function at many different levels that will help us to maybe come up with a better system, a better framework for thinking about how to intervene. I want to take just a few minutes and then to think about where we are in terms of therapeutics, because that's so much more complicated. The third point to say is that changing diagnostics helps us a lot with changing therapeutics. That's really the lesson we learned from oncology and other areas of medicine. But the other lesson that we're taking increasingly is that we have to get earlier in the game. When you look at our research in particular, but also our practice for psychiatry, we are real latecomers. And I mentioned this before when I talked about those changes in AIDS and cardiovascular deaths and the deaths from stroke. And one of the things that comes up over and over again is where we've had the most success in medicine is where we've been able to get into the game early. And by definition, we get there late in psychiatry. I want to be really clear about this because it's something that I didn't understand for a long time. But through the advent of imaging and other recent studies, it's become more and more clear to me that there are lots of ways to screw up your brain. And if you have a neurodegenerative disease, Alzheimer's, Parkinson's, Huntington's, you will have brain pathology for at least a decade. Brain pathology that is easily detected and that is profound before you have your first symptom. Parkinson's disease, you have to lose 80% of the nigra dopamine cells before you have slowness, rigidity, and tremor. At 70%, you're fine. And that takes about a decade. There's no reason to think that it's any different for schizophrenia or autism or mood disorders. By definition, it seems to me, this is still a supposition, but I think I can argue the case, behavior and cognition are late stages, changes in behavior and cognition are the last thing to go in brain disorders. So part of why we're rethinking mental disorders as brain disorders is to be able to move us to a point where we can get much earlier in the cycle. So in the case of psychotic illnesses, we define schizophrenia by the presence of psychosis. Too late. Mm-hmm. By that time, it's like defining ischemic heart disease by the presence of an MI. You want to be there earlier in the game. And so, and I know I'm preaching to the converted here, because there are a lot of people in the front two rows who are very committed to this. But the model would have us thinking much more about the prodrome, which we're dividing here into early at risk and late at risk, and figuring out how to develop preventive interventions well before, so that you begin to preempt rather than have to treat psychosis. want to drive down morbidity and mortality. And we don't know how to do this yet. We do need the biomarkers in this space. We do need much better kinds of diagnostics to do this, but we have many of the tools. I think I could show you that to begin to do that. What would the interventions look like? Well, they could be a range of things. They're not going to be antipsychotic medicines. We know that. We've actually tried that. It doesn't work. But you can imagine a whole range of things. We try to summarize this in a work group of our council that suggested different approaches to this, called From Discovery to Cure. Recent Nature piece on electroceuticals, which has gotten a lot of interest, the idea that we can begin to use devices to manage circuits, particularly for epilepsy, and perhaps for chronic pain, and maybe for cognitive disorders as well. I think many of you saw this piece from Nature a couple of weeks ago that came out of UCSF, Adam Ghazali's work on using video games to actually retrain the brain. It's the kind of work that Sophia and her colleagues have done here so beautifully. We've tried to summarize in various places what this new era of interventions might look like. To kind of cut to the chase, the concept is that we're not just thinking about the magic bullet or the small molecule that is going to be the solution anymore. We really have to, for these circuit disorders, get way beyond that and think about the ways in which we can use psychotherapy, we can use psychological or cognitive interventions like video games to begin to retrain circuits to make sure that we preempt these kinds of bad events like psychosis. I think for the sake of time, I'm not going to spend a lot of time on this except to say that in the kind of work that we're trying to fund in terms of treatment trials, we're really trying to move away from the exploratory trials, which have not really given us what we wanted, to studies that are much more about target validation and using clinical trials not to come up with a breakthrough new powerful treatment. That would be great, but we're not ready to do that. Using clinical trials to understand the disorder better. So this is a real shift in focus. So we call it experimental medicine. What we want to know about